So today's lecture, I'm going to start off with the little bit of revision of wave mechanics that we have done so far. So that if we are going to start with a little bit advanced, a little bit if you want to advance into one-dimensional potentials, we may need certain concepts of wave mechanics to be revised. So far we have seen that the Schrodinger equation Schrodinger equation for a non-relativistic particle moving in one dimension under the influence of potential Vx is a linear partial differential equation given by iota h ket del psi upon del t is equals to minus of h ket square upon twice m, and then you have this del square psi upon del x square plus Vx psi x. A similar equation in three dimensions would have been we would write as iota h ket del psi upon del t is equal to minus h ket square upon twice m, and then you have this, instead of t square you have del square psi plus v psi. Okay, and we have seen that this particular equation we try to derive it using the matter wave hypothesis. We have derived it initially. Now, this particular equation represents what? This particular equation represents a correct physical law of time evolution of this wave function psi. Okay. How can we determine its correctness? So question arises, how can we determine its correctness? So answer to this question is experimental validation. So whether this particular equation presents a correct picture or not, whether it presents a correct picture or not, of time evolution of psi or not, this can be settled by giving psi of x a physical meaning based on the solution, and then comparing this prediction with experiments. Okay. Now, till now, We have not seen any contradiction. So till date, whatever predictions we've been able to make using Schrodinger equation, predictions based on Schrodinger equation have been in consonance with all experimental findings. So till date, so this is how we do. Till date, we have not found any deviation from the experimental findings. So whatever prediction we make using Schrodinger equation, uh, we've seen till date that they have followed the experimental line. An important postulate we have seen till now, an important postulate we've seen in quantum mechanics, that each classical observable like momentum, energy, position, in fact, angular momentum, okay. Uh, so I'll write for each classical observable like momentum, energy, position, angular momentum. There corresponds an operator in quantum mechanics. There corresponds an operator in quantum mechanics, which acts on the wave function, Okay, so let's say we want to and accept the position operator. Other operators are derivatives, or you can say are differential operators, you can say. So for example, you want to find the position operators. Position operator is like x cap psi x is simply multiplying x by psi. And if I say what is px psi, it is equals to minus iota h cat del pi del x of psi. This is a postulate. Just remember, if I want to write the kinetic energy operator, then it will be equals to px square upon twice m if it is in one dimension psi. So basically minus h cat square upon twice m del square psi upon del x. Okay, now what is this psi? Psi is nothing but it is a mathematical construct. This is a mathematical construct which gives maximum information about the state of the system. Therefore, it is at times also referred to as state vector or state function. So this wave function psi is also referred to as state vector. We are going to see it in ket and Brun notation, or state wave function or state function, or simply wave function, right? Okay. At times it is fruitful to write. At times it is fruitful to write the state of function that is the wave function in as a function of momentum. Okay, so at times for a certain experiments, let's say scattering experiments, we have momentum profile. Okay, so in those cases, we may prefer to write the wave function in terms of momentum. Okay, and for that particular thing, an important thing would be to use the Fourier transform. So I'll write it here. An alternate way of an alternate specification, an alternate specification of the state of the system is via Fourier transform of the wave function. That is, by executing a Fourier transform, we can write our wave function as a function of momentum, as a function of momentum, or simply wave numbers. Okay, so how to do that? Basically, what we do, we take a Fourier transform. So basically, if you want to write our wave function in form of k, we'll take a Fourier transform of our wave function in position. And if you again want to write our wave function is position or in coordinate space, I'm going to again take a Fourier transform. Usually it is set as a inverse Fourier transform, but okay, that's fine. Both of them are Fourier transform of each other. Okay, and see, this particular thing I will write as psi of. So this particular thing, sorry, this particular thing I'm going to write as, I know that my uh, I know that my I can write my momentum P as h cat k. So basically here I can write it as P upon h cat, and this particular thing I can write it as dx e की power minus iota p x upon h cat, and then you have the psi x. So if you want to convert your wave function in coordinate space to wave function in momentum space, this is what formulation you can use. This is how you can do it, by taking a Fourier transform of the wave function psi x. And if you again want to write your psi x from coordinate space, so from momentum space, you can do this. Okay. Now, having said all these things, we also saw that what is your psi mod whole square. So what does your psi mod whole square represent? So psi mod whole square represents, so let's say it is in one dimension. So I'll write x comma t mod whole square. It represents what? It represents the probability density. It represents the probability density at point x or at position x and time t. Okay, so basically, and if I want to integrate it, I will get what? I will get my probability. So basically, your psi mod whole square dx from minus infinity to plus infinity will give you the probability of finding the particle somewhere in the space. And in fact, it would be unity, because somewhere in the space particle should be there. So probability of finding the particle somewhere in the space from x equals to minus infinity to plus infinity. Okay, and certainly this would be equals to 1. Okay, provided this size normalized. Okay, so that part also we are going to come. So if it is normalized, I'm going to write if size normalized. In terms of in language of linear vector space, we can write this particular thing as norm of psi. Okay, we've also seen that we've also seen a global conservation of probability. Global conservation of probability, by which I mean that iota h get del by del t of psi mod whole square dx is equal to 0. What does it imply? It implies that the total probability of finding anywhere, of finding particle anywhere in the space must be constant or must be constant. What does it assert? It asserts that if wave function is normalized at t equal to 0, then it remains normalized for all future times. For all future times. So why it is so? See, whenever we have to see, we have to find the normalization constant. So let's say A belongs to C, and if we want to normalize our wave function, so what do? We do this. We multiply with this, and we know that if we want to see that it is normalized, what we are going to do? We are going to take the norm and equate it to 1. By taking norm, if I say that my wave function is normalized at t equal to 0, and this particular thing, that is the norm of psi, does not change with time, then once I have normalized, it will remain normalized forever. So we don't have to find normalization constants at different time. It implies that if once you have normalized your wave function, let's say at t equal to 0, whatever normalization constant you found at that particular time t equal to 0, since this particular quantity, that is the norm of psi, does not change with respect to time, so therefore your normalization constant also does not change with respect to time. So normalization constant also remains intact. Although for unstable particle, we've seen all these things. I'm just going to revise all these things quickly. Although in the case of unstable particles, unstable particles, that is one in which you have some decays, or which disintegrate with respect to time. Okay. In that case, probability of finding the particle, since it is decaying, probability of finding the particle does not remain a constant. Rather, it decreases exponentially with time. Let's say this is t. This is with respect to time t. Exponentially with respect to time. Okay, this is what we have seen. So all these things are statements from global conservation of probability. While we were discussing global conservation of probability, so while deriving the global conservation of probability, we tacitly assumed that the potential energy V is a real function, is a real valued function. But if we add an imaginary part to it, if we add an imaginary part to it, that is the potential energy, then probability depends upon time. Okay, so your probability of finding the particle somewhere in the space does not remain a constant if the potential energy is not a real valued function. That is, if we add some imaginary part to it, then probability depends on time. Okay, so for unstable particles, one can expect that the potential energy would be a complex valued function. Now let us try to see some very standard functions. Let's say one of the wave function I'm giving you, just take time to find the normalization constant. I'm going to give you 1 minute. Try to do it. If you're not able to do it, I'm going to do it in 1 minute. So just 1 minute for you. Try to find the normalization constant. Okay, so how to find the normalization constant? It is quite easy. This A can be found by taking the norm. So I'll say that this norm of psi must be equal to what? 1. So let us take that. So that will be A mod whole square from minus infinite to plus infinite e की power minus 2 lambda x, because see, this is iota. So if I'm going to do this psi star psi in dx, this psi star would contain this iota omega t. So I'll have this iota omega t here. There would be some, let's say I'm writing it here, some function here, and then a star, sorry. And then you have this a e to power minus of lambda modulus of x, and then e to power minus iota omega t dx. This would get, this would become 1. And here you'll have a mod square e to power minus 2 lambda mod x equals to 1. From minus infinity to plus infinity, probability of finding the particle somewhere in the space should be equal to 1. From here, we'll get this. And this particular thing you can do by, since this is an even integral, so from 0 to infinite, e to power minus 2 lambda x dx is equals to 1. And then you can write it as this. This is 1 upon 2 lambda e to power minus 2 lambda x from 0 to infinite is equals to 1. So that implies your a mod should be equals to what? Root over lambda, sorry. So your normalization constant is root over lambda. So therefore your normalized wave function appears to be root over lambda e to power minus lambda modulus of x e to power minus of iota omega t. Okay, now in quantum mechanics, quite often we are going to see that we are using average values, that is the expectation value. And we've seen already that, see, we understand that wave function in space, let's say it is a Gaussian function. So it is going to give you some probability distribution of finding the particle in space. This psi, from this psi, you can find what is the probability of finding the particle somewhere in the space. And indeed, it is a probability distribution. Let's say Gaussian here for that matter. So you cannot know prior to measurement where your particle is. Let's say once you made a measurement and now let's say particle is here. So this particular wave function collapses to a spike. If we make another very quick measurement such that this psi does not involve, we'll get every time the answer as this measurement only. So in order to circumvent this, what do? We prepare an ensemble of particles in the same wave function and take the repeated measurements. In each measurement, we are bound to get some different value because after all, understand this, let's say only position, if I'm saying position itself is governed by a probability distribution. So what we are going to do, we are going to take average value, and that taking average is called as expectation values. So let's say, so again, I'm covering this up. See, your let us say position, let's say wave function is psi is equals to, let's say, e to power minus of okay, so let's say e to power minus lambda x. Okay, so I understand that psi mod whole square will give me the probability of finding the part as probability density. Okay, so it is governed by some probability distribution. Now we don't know prior to measurement where a particle is. We are certain that it is somewhere here, from here to here, from minus infinite to infinite. It is somewhere governed by probability distribution. So probability of finding the particle here would be maximum, and as we go along, the probability would decrease because the area is decreasing. Understand that once the measurement has been made, let's say your particle was here at C. So here you will get a narrower spike. Now, if you take a repeated measurement in a very quick succession, without wasting a lot amount of time, without giving a time such that this particular psi evolves, you're going to get the same result. You are going to get the same result. So therefore, what we do, we actually try to prepare an ensemble of particles prepared in the same state, and we do repeated measurements. And in those repeated measurements, we are certain that we are not going to get the same value every time. Okay? And we take some averages of all those measurements, and that is called as the expectation value. Okay, so just with regards to position measurements, I'm writing the expectation value at first, and then we are going to generalize it with every generalize it to every you can say operator corresponding to the dynamical observable. So if we wish to do position measurements, if we wish to do the position measurements on a large sample of electrons, all prepared in the same all prepared in the same state, all prepared in the same state, we would get different results. We would get different results. Why would get different results? Because your wave function is also evolving with respect to time, and in space, your wave functions psi is both function of x and t. You don't know where your particle is. So let's say if I'm creating an ensemble of particle, all are in the same wave function, all are prepared in the same state. Let's say this, you don't know where a particle is, here, where. So your each position measurement will give you a different spike, and all these spikes, we take these average values of these measurements, and that particular average is called as your that particular taking average is called as your what you can say expectation value. We would get different result in each measurement. In each measurement, since the wave function also evolves with time, therefore in quantum mechanics we rely on expectation values. Expectation values. We rely on expectation values. Is that clear? I think this is quite clear to you. For particle in state psi, the expectation value of x is given by minus infinite to infinite x psi x comma t modulus whole square dx. This is how you get the expectation value of x. Okay, and please do understand, this is quite a confusion that usually people get. Understand that expectation value is the average of repeated measurements on an ensemble of what you can say identically placed or identically prepared systems, and not the average of repeated measurements on one and the same system. Please do understand this point. Okay, so this is one thing that you should remember now. Okay, in general, if you want to write the expectation value of an operator, let's say A, what do we get? This is equal to integration minus infinity to plus infinite psi star A cap psi dx divided by minus infinite to plus infinite psi mod whole square dx. This is how you define your expectation value of any operator corresponding to the dynamical observability. So let us take the same wave function that we did take before and try to find the expectation value of x and x square. Okay, so let us take the same wave function psi of x is equals to a e की power minus lambda modulus of x e की power minus iota omega t, and we know that this a we have found already, it is equals to root over lambda. This normalization we have already found. We want to find the expectation value of x. How to find this expectation value of x? So your expectation value of x is minus infinity to plus infinity x a mod whole square e की power minus 2 lambda mod 2 lambda modulus of x, and then this dx in this particular time factor, time dependent factor goes away, because you know that if I want to find this would be psi star x psi dx from minus infinity to plus infinity, and you understand that psi star would give you e की power iota omega t, and here you will have e की power minus iota omega t. So you are only left with the time dependent, space dependent function. So this is like this from 2 root over lambda root over from 0 to, so not even root over lambda, it would be simply lambda x. And then you have this x into, okay, you could have taken right this way also, minus infinity to plus infinity. You can take this this also, minus infinity to plus infinity x into e की power minus 2 lambda modulus of x. Just see this particular thing is an even function, this particular thing is an odd function. So overall, this particular integrand is an odd function. This particular integrand is an odd function. And if I'm integrating it from minus infinity to plus infinity, this particular thing would come out as 0. Because you remember that if I integrate from minus a to a, your odd function, f of x, then this is 0. And if I integrate from minus a to plus a f of x dx, and your f of x is an even function, then this is 2 times 0 to a f of x dx. This is something that you've already studied. So you know this expectation value of finding x would be simply 0. What do you think the expectation value of x square be? Just try to find it. I'm giving you a minute. Okay, so before doing that, just try to remember one formula. If you don't remember, then I'll write it here. So if you want to find, let's say, integration from 0 to infinity, x की power n, here n belongs to natural, and e की power minus of ax dx, then you can write it as n factorial divided by a raised to power of n plus 1. This is simply finding the Laplace transform. So if you don't remember this, I have given you this hint. So please do remember, every time I'm going to give you a question, if there is a difficult integral, I'm going to write the integration sideways so that you just can use that particular integration before exams or anywhere. If you're studying in MSc or if you're doing some exam also, please try to remember these formula, because in exam you'll not be able to derive all those things. Okay, so this is a recommendation. So how would you find this x square? The expectation value of x square would be minus infinity to plus infinity. This is x square. This is root over, sorry, this would be, I think, lambda e to power of minus of 2 lambda modulus of x dx. And from here, you know, this thing you'll get as 2 times lambda integration from 0 to infinity x square e to power minus 2 lambda x dx. And this is equals to 2 lambda times, you know, this is your 2 factorial. And instead of a, you have 2 lambda. So you have 2 lambda raised to power of 3, because 2 plus 3 is 3. So I think you will get an answer as this is 4. This is 4 divided by 8. This is 1 upon 2. This is lambda and this is lambda cube. So this is lambda square. This is it. So 1 upon 2 lambda square would be the expectation value of x. One of the most important results that we are going to see later on also in quantum mechanics is called as the Heisenberg principle of uncertainty. Although we are going to see all these things in detail, right now, I'm taking what you can say Mermin's approach, which is called as shut up and calculate. So right now, just focus on doing this quantum mechanics. All these difficult questions, like really understanding the meaning of, physically understanding the meaning of Heisenberg principle of uncertainty and wave packet, all these things I'm going to create some lectures separately. Then there you'll be able to understand what all these things in greater detail. But right now, just I'm introducing you something called as uncertainty, something called as uncertainty. For the disturbance, uncertainty. Okay. So I'm writing it here. An important principle in quantum mechanics is Heisenberg uncertainty principle. And what does it state? It states that the uncertainty delta x, that is in position, and p, their product is always greater than equals to h cat by 2. Statistically, we write this as sigma x, which is the standard deviation, and this as sigma y, which is the standard, sorry, sigma p, which is standard deviation in momentum. The lower bound is equals to h cat by 2. Okay, and what precisely does it wants to say? It wants to address that in quantum mechanics, in quantum mechanics, position and momentum of quantum mechanical particle cannot um, be simultaneously uh, simultaneously measured with arbitrary precision. And mind you, this is something inherent. This is something inherent to your system, like quantum mechanical systems. It is not. It is not a lacuna of experimentation. It is lacuna. It is in general uh, law of the land for your quantum mechanical objects. This is something that we are going to see separately. But just remember this particular thing, standard deviation sigma, is nothing but it is equal to root over. Let's say if I want to find in x square minus this is it. If I want to find, let's say, if I want to find my delta x in the case of uh, wave function psi x is equals to a e की power minus modulus of lambda x e की power minus iota omega t, what it would be. So what would be the uncertainty in finding the position? So uncertainty delta x is given by the sigma x, which is standard deviation. It is equals to root over x square expectation value minus expectation value of x whole square. We understand, we found that expectation value of x is simply 0, and expectation value of x square is equals to 1 upon 2 lambda square. So if I use this, I'll get the uncertainty in the position measurement, and which is equals to 1 upon 2 lambda square, and this root over it will be equals to 1 upon root 2, and you will get a lambda here. Okay, I'm not delving in detail, but just so till now we've seen one wave function psi of x, which was equals to a e की power minus lambda modulus of x e की power minus iota omega t. We found what is the normalization constant. A was coming out as equivalent to a was coming out to be equals to root over lambda. We found that the expectation value of x would be 0. We found that the expectation value of x square is simply 1 upon 2 lambda square. And we also found what is the uncertainty in finding the position, delta x, that is given by sigma x, and that is equals to what? It is equals to 1 upon root over. If I want to plot it for lambda equal to 0, so let me try to plot. Okay, let me try to not try to plot the, instead of this, let me try to plot the probability density. So let me try to plot the probability density as a function of x. I know the probability density psi mod whole square is simply psi star into psi, and which is simply a mod whole square e की power minus 2 lambda modulus of x. And we know that this mod a square is root 2, sorry, this is lambda e की power minus 2 lambda modulus of x. So how do you plot it? I can plot it in this fashion. You know that for x greater than 0, so I'll just write first this. This is how I can draw my e की power of. So your mod x, mod x can be, mod x can be minus x if x is less than 0. So I'm just writing it here. So how your wave function would behave? Your wave function psi x would be simply lambda e की power 2 lambda x if x is negative. Because if x is negative, then your mod x becomes minus x. And if your x is positive, then this becomes this. So, so I'm just making a graph of 2. So this is e की power of 2 lambda x, and even if you multiply lambda, not much is going to change, only there would be shift in this particular thing. Okay, so this will be 0 comma lambda here, and this will be lambda e की power minus 2 lambda x. So clearly from this particular description, you know that for all x less than 0, we have to trace the graph of lambda e की power 2 lambda x, which is this, and for all x greater than 0, I have to plot lambda into e की power minus 2 lambda x, which is this. So eventually, I know my graph for psi mod whole square as a function of x would be this. Now I'm giving you a question, a simple question. What do you think is the probability of finding the particle from sigma to infinity, where sigma is, sigma you already know. What is sigma? Sigma we've already found. Sigma was, I think, 1 upon root over 2, and this was lambda, I guess. So the probability of finding the particle from sigma to infinity would be, or sigma into infinity, and you can say probability of finding the particle, from outside minus sigma to plus sigma. So what sigma was representing? Sigma was representing the uncertainty. So beyond this uncertainty thing that you found, that is sigma, what would be the probability? The probability would be simply this area, and this area. So let's say this is your minus sigma, this is your plus sigma. What is the probability of finding the particle outside minus sigma and plus sigma? It would be simply this integration, and this integration represents this area. So this would be simply, I think, from minus infinite to minus sigma, Sine mod whole square dx, and then plus sigma to infinity, Sine mod whole square dx. And we know that Sine mod whole square is an even function, so simply I'm going to write it as 2 times integration from sigma to infinity, and this will be Sine mod whole square dx, which would be simply 2 times integration from sigma to infinity, and you will get lambda e की power minus 2 lambda x dx. I think this is easy to find, that this will be equals to 2 upon 2 lambda, and the lambda is already here. This is e की power minus 2 lambda x from sigma to infinity. I have taken a negative common, so I'm going to get this 2 gets cancelled. And from here, I know this sigma is 1 upon root 2. So this is, I think, answer will be 1 upon e की power of minus of root 2. Because this is 1 upon root 2 lambda, lambda gets cancelled with this. And I think it is almost equivalent to, if I calculate, this is equals to around 0.24331. So probability of finding the particle outside this, what you can say, I would say that zone of uncertainty, because what is sigma? Sigma is going to give me this sigma is a standard deviation in the measurement position. So beyond this minus sigma comma sigma, probability of finding the particle would be simply 0.24331. See, one of the important concepts, I'm just going to list it here. I'm going to just show it using one example. This question was asked in TFR 2014. And instead of x, they asked the position, the expectation value of momentum. Now, the question says that a particle is moving in one dimension and has the unnormalized wave function given by where lambda belongs to R, then the expectation value of momentum is, see, whenever you are supplied a real wave function, and you are asked about the expectation value of momentum, it is always equal to 0. It is always equal to 0. Why? Just I'm not writing a brief, I'm not writing a complete proof, but just understand that what is expectation value of P? Expectation value of P would be minus iota h ket. From minus infinite to plus infinite, it would be psi star. And then this will be, sorry, del by del x of psi dx. Understand that expectation value is after all an average value. And so therefore expectation value must belong to real number. It should be real entity. See, this is, in any case, this wave function psi is real. So this remains real. The derivative also remains real. And the psi star also remains real. So this particular integration, you will get some real answer here. Expectation value has to be real. Here you see there is a term minus iota h ket. So if anything you get, let's say any non-zero value you get from this particular integration, you will get the expectation value to be imaginary, which cannot be the case. So therefore, it implies that expectation value should be equal to 0. That is, this integration should come out as 0. Because only then your expectation value will remain real. Otherwise, you see, if any non-zero answer you get from this integration, you will get a complex answer as expectation value. So always remember that the expectation value for momentum for real wave function is always 0. So I hope you've learned enough in this particular lecture. I've tried to revise all those concepts since I was not taking class for a while now. So please revise all these lectures. I'm going to meet you in a second lecture, which is again going to be a brief revision of wave mechanics. Till then, take care.